Today we'll be looking at space physics in the last chapter of Cambridge Igcse, and we'll be looking at the subsection we'll be looking at is the light speed calculation. We'll be taking a look at the light speed. So before we begin, let's take a listen to this tutorial.
In this video, we'll look at distances on an astronomical scale, including calculations involving the speed of light. Light travels through space at a speed of 300 million meters per second. That's 300,000 kilometers per second, or 3 times 10 to the 8 meters per second. That's 3 followed by 8 zeros. The speed of light is constant throughout the universe. It is the fastest known speed, and nothing can travel faster than this. Calculations involving light years require the use of the familiar equation speed equals distance over time. For example, light from the sun takes 8 minutes to reach the Earth, which is at a distance of 1.5 times 10 to the 11 meters. Take some time to get familiar with your calculator if you haven't already. Using the scientific notation button will save you a lot of time compared to typing out every zero. Let's put this into practice. The mean distance between the Sun and the Earth is 1.5 times 10 to the 11 meters. Light travels at a speed of 3 times 10 to the 8 meters per second. Calculate the time taken for light from the Sun to reach the Earth for 3 marks. To calculate the time, we rearrange the equation speed equals distance over time to give time equals distance over speed. If the distance from the Sun to the Earth is 1.5 times 10 to the 11 meters, and the speed of light is 3 times 10 to the 8 meters per second, then t equals 1.5 times 10 to the 11 over 3 times 10 to the 8. This gives 500 seconds, which is about 8 minutes. Let's try a slightly harder example. Radio waves from Earth take 5.1 minutes to reach Mercury, and 5.4 hours to reach Pluto. The radius of Mercury's orbit around the Sun is 5.8 times 10 to the 10 meters. Calculate how many times further away Pluto is from the Sun than Mercury. First, let's sketch out the scenario. We have the Sun, Mercury, Earth, and Pluto. We know that Mercury is 5.8 times 10 to the 10 meters from the Sun, and that light takes 5.1 minutes to travel from Earth to Mercury, and 5.4 hours to travel from Earth to Pluto. We want to find the ratio of the distance between the Sun and Pluto and the distance between the Sun and Mercury. From the equation relating speed, distance, and time, and from the fact that the speed of light is a constant, we find that time and distance are directly proportional. This means that the ratio of the distances is equal to the ratio of the time. Therefore, we can work out the values of time, and we don't have to convert to distance. But we do have to convert the times into the same unit. For ease, minutes will be the simplest. The time for light to travel between the Sun and Mercury is 5.8 times 10 to the 10 meters, divided by the speed of light, 3 times 10 to the 8 meters per second, which gives us a time of 193 seconds. Then, dividing by 60 gives a time of 3.2 minutes. Next, we need to convert the time for light to reach Pluto from Earth, 5.4 hours, into minutes. This is simply 5.4 times 60, which is equal to 324 minutes. So now we can see the total time for light to reach Pluto from the Sun will be the sum of these 3 values, which is 332.3 minutes. Therefore, the ratio of the travel time from the Sun to Pluto and the travel time from the Sun to Mercury is 332.3 over 3.2, which equals 104. This means that Pluto is 104 times further away from the Sun than Mercury. In summary, astronomers use light years as a unit of distance between interstellar objects. The familiar equation speed equals distance over time can be used in calculations involving light in the solar system. This uses the fact that the speed of light has a constant value of 3 times 10 to the 8 meters per second everywhere in the universe. Don't forget to check out all of our other fantastic revision resources.
Okay, so we just seen the tutorial on calculation involving time, speed, and distance. Okay, the same time, distance, we're going to employ for solving problems in the space. Okay, now the first thing we need to know is that light is the fastest thing on Earth, and light is a wave. It's a type of electromagnetic wave, and it has a constant speed. It travels at a constant speed of 3 times 10 or 3.0 times 10 to the power of 3 times 10 to the power of 8 meters per second. Okay, so this is the speed of light in space. Okay, this speed can be put as 3 with 8 zeros, which means 300,000 kilometers per second. If you want to make it kilometer per second, this meter, okay, this kilometer per second. First, let's make it meter per second in numbers. Okay, we have 300 million. Okay, this is 300 million meter per second. So in 1 second, second is like a blink of an eye. In 1 second, light will travel 300 million meters. 300 million meters. If you put in kilometers, it will be 300,000 kilometers in 1 second. 300,000 kilometers. Okay, a car running at 150 will even take probably 1 hour to even travel a distance of just a few kilometers, less than 100 kilometers. Okay, we take such an hour to reach 100 kilometers or 120 kilometer distance. Can you imagine 1 hour to reach just 100 or 120 kilometers? Okay, 1 hour to reach. That's if the car is moving very fast. To reach 100 kilometers, you take an hour. An hour means 60 times 60. If you change to seconds, 60 multiplied by 60, which is 3,600 seconds. This will be equal to 3,600 seconds. Okay, this is what it takes a fast-moving car, to cover just 100 to 120 kilometers. But look at what light in 1 second. In 1 second, see what it takes, like 300,000. 300, not just 100, 120 kilometers, 300,000 kilometers in just 1 second. Just 1 second. So that, if you can imagine this, you can pause for a minute and imagine this, you'll see how fast light is. Light is the fastest thing on Earth, and it takes only 8 minutes from light to come all the way from the sun to the Earth, a distance of 1.5 times 10 to the power of 11 meters. A distance of this. If you put it in real number, you see this is almost 1 trillion 500 billion. 1 trillion 500 billion. A distance of this. It takes only 8 minutes for light to travel all the way from the sun to reach us. Only 8 minutes. Okay, light will travel from the sun to reach us a distance of 1 trillion 500 billion meters. So such a huge distance. It takes light just a few 8 minutes. Light will travel all the way from the sun to the Earth. Is that okay? So, and this is what you need to. These are the things you need to. You need to know the speed of light in space. Okay. Now let's take a look at. It takes time for light to travel such a large distance. If you have a very large distance, like from the sun to the Earth, is a large distance. It takes time, but it only takes like 8 minutes for light from the sun to reach the Earth. Only 8 minutes. Only 8 minutes. And the distance from the sun to the Earth is very long. If you go to travel with a car to the sun, you probably take more than 10,000 years to reach the sun. If you go to travel with the car. So, however, it takes light only 8 minutes to reach us from the sun. And it takes around 5 hours for light from the sun to reach the outer regions of the solar system, like the Pluto and all the outer region. It only takes like 5 hours. Light will reach every outer region of the entire universe, of the entire solar system. And it takes only 4 years for light from our nearest star, the nearest star, which is the sun. The sun is one of the stars. In fact, is the smallest stars. Okay, there are bigger stars. When you go beyond the sun, there are bigger stars, and billions and billions or zillions of stars makes the galaxy, and zillions of galaxy makes the Milky Way, and billions and zillions of Milky Way makes the first level of the lower heaven, of the first heaven. Okay, so to reach the Earth, it takes about 4 years for light from the nearest star, which is the sun, to reach everywhere on the Earth. Okay, now the Milky Way galaxy contains billions of stars. Okay, the Milky Way galaxy is the biggest. We have galaxies which makes up the Milky Way, and then the Milky Way contains billions of stars and billions of galaxies. And we say the Milky Way is the biggest of the stars, or the biggest of the galaxies, and it has a very huge distance away from us, very super huge away from us, with the light taking even longer to reach from the Earth. Okay, from that side to the Earth, it takes a longer, of course, because the Milky Way is super far away. The sun, as far as we say the sun is to the Earth, but it's still considered not so far if you compare it with what? With the stars, with other stars. As you move up the stars, the higher you go, the bigger the stars are. Okay, the sun is one of the smallest stars that has been given to us to regulate our day and night. That has been given to us by the creator of the universe to regulate our day and night. It is the sun that determines the morning time, afternoon time, evening time, and night time, and when we go to bed. It is this alteration and algorithm that has been formulated by the creator of the universe that has enabled us to have this life that we have. Okay, so the sun is a very special parameter in our very existence. It is very special parameters. It is what determines the rise and the fall. The rise and fall of every day. The daytime, the outbreak of the day and the night, the interception of the day and the night, the alteration of the day and the night is a functionality of the sun's commonality and behavior. Okay, so now to calculate the distance, the distance, the unit of years or distance is called the light year. The unit of distance in this regard, because the distance is so huge, we no longer use meters, we no longer use kilometers. It's so huge, especially if you're in the Milky Ways on the galaxy or in the first lowest heaven, the first heaven, the lowest heaven. The distance is so huge away from us that if you start using meters and kilometers, it's like you cannot calculate the numbers. So we start using light year. Now to carry out the light speed calculation, we use the normal speed equation that we know that the average speed is total distance over total time taking. So we use the normal speed equation we know from the elementary physics, from the beginning of physics. We use that same concept to say that our average speed is the total distance over total time taking. The average speed is the total distance. Let me just write distance, okay? But you know what it means by total distance. That means all the distance that you have traveled over all the time that it takes, okay? Over all the time that it takes. So we say average speed is total distance over time taking, total time taking. So it is this same elementary physics formula that we use for outer space calculation. Here you can make, if you're looking for time will now be, will be distance over speed. You cross multiply and make time the subject. It will be distance over speed. And if you're looking for distance, you cross multiply, it becomes speed times time. If you're looking for speed, it's distance over time. Okay, so this is what it takes and what we will use in our calculation. Now let's take a look at one example. It says the radius of the Mercury orbit around the Sun is 5.8 times 10 to the power of 10 meter. The radius of Mercury's orbit around the Sun is this. Now the speed of light is always constant, even if they don't tell you. 3 times 10 to the power of 8 meters per second. Calculate the time taken for light from the Sun to reach Mercury. You already know time is distance over speed. Time is distance over speed. So we bring out the parameter. Distance is given to be 5.8 times 10 to the power of 10. And our speed is 3.0 times 10 to the power of 8. Now, then we write down our formula. The next step is time is the distance over speed. Time, you make time the subject of formula from the original equation. Distance over speed. And the distance, remember, is 5.8. You put it down 5.8 times 10 to the power of 10. Divide by the speed, which is 3.0 times 10 to the power of 8. We get 192 seconds. So it takes 193 seconds for light to travel from the sun to the Mercury. Okay? To the Mercury. It takes, for this particular calculation, for light to travel from the sun to the Mercury. Okay, now let's move on to the next one. Okay. Okay. Now, before we look at this section or segment is called the gravitational field strength of a planet. You know, we say this planet we are in is controlled by gravity, force of gravity, right? How much of that strength does your gravity have? Why is it that everything we throw up, if you throw anything upward, it must come down. It will not continue to go up. If you throw a stone up, the stone will still eventually come down. Anything you throw up, instead of it to be going the outer space, it will still come down. We say this effect is as a result of the gravitational field strength. Gravitational field strength, in fact, is the reason why we're able to walk on Earth. There's a force, a field that is acting always towards the center of the Earth that keeps us firmly on the ground. Now, we want to look at this gravitational field strength and how strong it is. In our universe, we call it G. G equals to a constant value of 10 Newton per kilogram. Okay, that's the value we use for it for our Igcse program. But before then, let's take a look at this tutorial and see what we need to know.
This video is about the orbital motion of the objects in the solar system. The planets in the solar system orbit around the Sun in nearly circular paths. In order to maintain these circular paths, there has to be a force keeping them in orbit. This is called a centripetal force. The centripetal force that keeps the planets in orbit is the gravitational attraction of the Sun. This force always points towards the center of the circular path and acts at right angles to the velocity. When showing the gravitational force acting on an object, always draw the arrow from the smaller body to the larger one. This is because gravitational forces are attractive and always act towards the center of the larger body. The size of the gravitational force between objects depends on the size of the masses involved. This means large masses such as stars and planets produce large gravitational forces. The Sun contains over 99% of the mass of the solar system. Therefore, it produces the largest gravitational force out of all the objects around it. The size of the gravitational force also depends on the distance between the masses. As the distance between the objects increases, the smaller the effect of gravity becomes. The planets closest to the Sun experience the strongest gravitational attraction, whereas the outer planets experience the weakest. This reduced force has an effect on the orbital speed of an object. The weaker the force, the slower the orbital speed. Therefore, the planets closer to the Sun travel faster, and the planets further away from the Sun travel slower. Make sure you can explain how orbital speed decreases with distance, as this can come up in an exam question. Let's try an example question. Two satellites, X and Y, orbit the Earth at different heights above the surface, as shown in the diagram. Compare the orbital periods of X and Y. So, for 3 marks, we need to compare the two satellites, X and Y, in terms of their distance or height above the Earth, their orbital speeds, and their orbital period. First, let's pick one of the satellites to focus on. and first look at its distance above the Earth's surface. Satellite X is further from the Earth than Y. This is a simple observation, but it is an important point and makes it clear to the examiner which satellite you are focusing your explanation on. We know that gravitational field strength decreases with distance, and that force is proportional to speed. So, as the distance from the Earth increases, orbital speed decreases. This means satellite X has a slower orbital speed than Y. And finally, as distance increases, orbital period increases as speed is inversely proportional to time. This means satellite X has a longer orbital period than Y. This makes sense because satellite X has a much longer orbital path around the Earth than Y, so naturally it will take X longer to complete one orbit. In a compare question, you have to write down similarities and differences between two objects or things. Make sure you refer to both of them to get all the available marks. In summary, gravitational attraction is responsible for orbital motion. The gravitational force always acts towards the centre of the circular path, from the smaller mass to the larger mass. The size of a gravitational force depends on an object's mass. The greater the mass, the greater the gravitational force it produces. The strength of a gravitational field also depends on the distance between the masses. As distance increases, the gravitational force decreases. The orbital speed also decreases, and the orbital period increases. Don't forget to check out all of our other fantastic revision resources.
Okay, so we just got rid this tutorial regarding the gravitational force and with relation to the distance, the orbital speed and orbital period. Okay, so when we increase when the distance is small, or when the distance away from objects are very large, then when the distance are large, the gravity will reduce. The gravity will reduce. The closer two objects are, the bigger the gravity. The bigger the gravity. So speed will also reduce, but orbital period will increase. The time period will increase, because period is like time. Okay, we increase. Okay, so that's all you need to know for this one, but let's quickly round it up. The gravitational field strength of a planet. Now we say the strength of the gravitational field around a planet depends on these factors: the mass of the planet and the distance from the planet. Okay, the bigger the planet, the bigger the gravitational field. Okay, it has. And then the distance. If the distance is close, it has a greater gravitational field. If the objects in the planets are farther apart, it has a less gravitational field. Now, the gravitational field strength and mass, let's take a look at that. The relationship between the field strength and the mass. Now, the relationship between the gravitational field strength and mass is given in this summative form. That the greater the mass of a planet, the greater the strength of the gravitational field, which we already mentioned. For example, the sun is the largest of all the things in our solar system. Of all the components in our solar system, the sun is the largest. So hence, the sun has a greater gravitational field. Okay, it has a greater gravitational field. About 203 Newton per kilogram. That's the gravitational field of the G value of the sun. It's about 293 Newton per kilogram. Now Jupiter, apart from the sun, Jupiter is then the largest apart from the sun, which has a gravitational field of 24.7 Newton per kilogram. The Saturn is there follows 10.5 Newton per kilogram. The Earth is actually, okay, we've not reached the Earth. The Uranus is 9 Newton per kilogram. The Earth is 9.8 Newton per kilogram, which we approximate to be 10, approximately for easier calculations. Okay, so the smaller the gravitational field. So one of the factors, the bigger the size, the bigger the size of an energy, the bigger the gravitational field. And this is how time is being calculated. The bigger the planet is, the bigger the force of gravity. And the bigger the force of gravity, the slower the time. the slower the time period, the smaller the time period. This is why I always say, if you do space physics, you understand why time in heaven is slower than time on earth. You understand why the time in heaven, because they have a very huge gravity. So when your gravity is very large, time in that universe will be very slow. Time in that universe is very slow. So if you are in first heaven, time will be slow, way slower than earth. Maybe 1 hour will be almost like 50,000 years on earth if you're in the first heaven. If you're in the second heaven, it's even slower, because the second heaven is way bigger than first heaven, and the time will be way slower. Third, bigger than second, way slower. Time will be smaller. If you're in fourth, fifth, sixth, seventh heaven, time will be way slower, and it takes few seconds for what you see as forever on earth. And if you are in the throne of Allah, or throne time, we are using the throne time, you see 1 second will be about 27,000 years on earth. 1 second will be about 27,000 years on earth. So the bigger the weight of the planet or of the universe you are talking about, the bigger the gravity. And the bigger the gravity is inversely proportional to the time period. The bigger the gravity, the smaller the time period. The bigger the gravity, the smaller the time period. So if G is very big, G is inversely proportional to the time period. Or we can use F here, force, because it's called gravitational field or gravitational force. It's inversely proportional to the time period. So you'll be wondering, if they tell you, if you go to outer space, if you spend several hours in the outer space, only several hours. If you spend several hours in the outer space, we're not even saying if you are in the Milky Ways. If you are in the outer space, if you spend several hours, it's like you spend more than almost 200 years on Earth. Like almost 200. If you spend several hours there, when you come back to Earth, you will not meet all your generation, all the people you left behind. Even your children must have passed away. Your grandchildren, maybe you meet on Earth, they must have passed away. And you still be looking young. So if you want to look here, you can go to outer space and live there for like few hours, 3-4 hours, and then come back to Earth. And then when you see that there you go again. If you want to stay 1,000 years, you can just follow NASA, in the United States, join the NASA astronaut, be an astronaut. You go there, spend like 3 hours, come back, you see that all your generation, they're gone. They died. And then you go again, you spend 3 hours, you see that you come back, all your generation, they've gone. So in this way, you'll be able to live like 1,000 years. Okay? So the point I'm making, the bigger the gravity, the smaller the time period. Okay? That's the point I'm making. The bigger the gravity, the smaller the time period. So they'll be wondering when they say, in heaven or in the heavens, time is slower. You'll be wondering why. It's because the universe there is way bigger than the Earth. In fact, the sun is 1,300,000 times bigger than the Earth. Can you imagine that? The sun is 1,300,000 times the size of the Earth we are living. The Earth is big. You can imagine this. It contains about 8 billion, approximately 8 billion people. But we're telling you, as big as the Earth, that you have to take aeroplane to fly for 20-something hours to reach some other countries. Even 20-something, 30 hours to reach some other countries in flying. As big as the Earth, we're saying that the Earth is a tiny dot compared to this tiny dot compared to the sun. The sun is 1,300,000 times, meaning you take 1,300,000 Earth to fit the sun, to fit it to the sun. Let's say this is the sun, the Earth is just this dot. The Earth is just this dot. Okay? The Earth is just this dot. You take 1,300,000 Earth to fit the size of the sun. So you can imagine that. And then we are telling you that the sun is the smallest stars that Almighty God created. You can imagine that. The sun is the smallest stars that God created. There are way bigger stars out there than the sun. Just that they are farther away. They're very far away. That's why they appear to be small when you look at the stars at night. They're farther away. So far, beyond the distance from the sun to some of these stars is unimaginable and unimaginable. So, And there are billions of these huge stars that makes up your galaxy. And there are zillions of galaxies that makes up your Milky Way. And there are zillions of Milky Ways that makes the canopy of the lower heaven. So you can imagine we are tiny dot. We are nobody in the sight of our Creator. We are nobody in the sight of the Creator. Okay? Now let's move on quickly. So let's take a look at the gravitational field strength and the distance, G and distance. The relationship between the gravitational field strength and distance is given as that if the distance, as the distance of the planet increases, the gravitational field strength decreases. If distance decreases, this one decreases. That means they are inversely proportional. So the gravitational field strength and distance, they are also inversely proportional. Because if one increases, the other one decreases. If one increases, the other one. So if the farther away, the smaller the gravitational field. Okay, maybe from the sun, for example. The farther away from the sun other planets are, away from the sun in the solar system, the smaller the gravitational field. The farther away, the closer to the sun, the bigger your force of gravity. So it kind of makes sense. Okay, so gravitational field strength is inversely proportional to distance and also inversely proportional to, but it's directly proportional to speed. It's directly proportional to speed. Okay, so let's move on. We say as the distance increases from the planet increases, the strength of the gravitational field decreases. Yes, distance is inversely proportional. Let's take a look at gravitational attraction of the sun. Now, orbital motion is a result of gravitational force of attraction acting between the two bodies. So the attraction is the motions of the objects moving in the orbit is as a result of the attraction of the force of gravity. So as a result of the attraction of the force of gravity that keeps them in that constant motion. Now the gravitational force always acts towards the center of the larger body. Always act towards the center. For example, we are a body on Earth. We are a body on Earth. Our force of gravity is always acting towards what? The center of the Earth, because Earth is the larger body compared to us. We are on Earth. So if you compare our force of gravity, it will be acting towards the center of the Earth. That of the Earth to the Sun, it will be acting towards the center of the Sun. If you're comparing the Earth and the Sun, the force of gravity of the Earth will be acting towards the center of the Sun. In other words, the gravitational field strength will always act towards the center of the larger body. And also, it causes the orbiting object to move in a circular path. It will make the orbiting object to start moving in a circular direction. The object will be moving, for example, if this is the planet, the object will be moving in a circular direction. At every point, it will be moving in a circular direction. Okay? At every point, this is the speed. Okay? At every point, we'll be following the orbit and moving in a circular direction. Okay, now let's move on. So the sun contains most of the mass, of course, about 99% of the whole masses of the solar system. The rest of the planet, they're only sharing less than 1%. Can you imagine that? The rest of the eight planets we're talking about in the solar system, they're sharing the mass they're sharing is less than 1%. When you say Mercury, Venus, Earth, all of them, Mars, Jupiter, whatever. If you count all of them, their whole masses, to tell you how big the sun is, the mass of all the 8 planets, is less than 1%, and the sun is greater than 99%. The sun is the mass of the sun. This is the sun. Okay, the mass of the sun is greater than 99%. Greater. So I use the greater than sign. Greater than 99% of all the masses of the whole solar system. While all the 8 planets, they are only sharing less than 1% of the masses. Only sharing less than 1%. All the 8 planets are sharing less than 1%. Even if you say Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranium, Neptune, and all of them, their masses put together. Remember I told you that the sun is 1,300,000 times bigger than the size of the Earth. So you can imagine that. So if you take all the 8 planets, put them together, their masses is around 1%, which is even less, maybe 0.9. less than 1%, compared to only Sun that has greater than 99% of the masses of the whole solar system. So that can give you a picture of how big the Sun is. How big the Sun is. The Earth is nothing to the Sun. The size of the Earth is nothing. It's just like a ring in the desert, in the Arabian desert. If you drop in, or in the Sahara Desert, it's even the biggest desert. If you drop a ring in the Sahara Desert, you're not going to find a ring. If from the aeroplane you just drop a ring randomly in the Sahara Desert, they ask you to come down and the whole Sahara Desert search for the ring. You'll never find the ring. You'll never find the ring. Okay? So that's what the whole planet is to the Sun, or the Earth is to the Sun. The Earth is infinitesimal. So the mass is nothing compared to the Sun. The Sun is nothing compared to the big stars out there. The big stars are nothing compared to galaxy. Galaxy is nothing compared to Milky Way. Milky Way is nothing compared to first heaven. First heaven is nothing compared to second heaven. Second heaven is nothing compared to third. Third is nothing to fourth. Fourth is nothing to fifth. Fifth is nothing to sixth. Sixth is nothing to seventh. Seventh, all the seven heavens put together, they are nothing compared to the Arsh of Almighty God. And the Arsh is nothing compared to the Kursi. Kursi is nothing compared to the Creator. So you can imagine this. And yet we are not focused. We are not focused. We have to be focused. And we have to do science to understand the wonders of the Creator. Okay, now we say the object orbiting around the Sun, the Sun's gravitational attraction keeps them in that orbit. It is that force from the Sun that keeps the object to be orbiting in that orbit. Now the force is directed from the orbiting object to the center of the Sun. The force of the object that is orbiting in any satellite or in any orbit is directed to the center of the Sun. Now let's take a look at this, what we have here. This is the Sun. These are other planets like the Earth. See the Earth as it moves around the Sun. Now you can see from here to the Earth, we have a force from the Earth towards the center of the Sun. From the Earth towards the center of the Sun at angle 90. And this is the speed. This arrow is always showing the direction of the speed. But it's always constant because it's moving a circular path. It's always constant because it's moving a circular path. And then this is the force of attraction, or the force of gravity, gravitational force, that is always acting towards the Sun. Remember I said, when two objects are acting, the force from the smaller one will always act towards the center of the larger one. First, I use the us and the Earth. For us, our force of gravity will act towards the center of the Earth. Comparing Earth to the Sun, the force of gravity of the Earth will act towards the center of the Sun. Okay, so this is very important, and we need to keep this in mind in order to be able to understand the space physics and be able to become astronaut if we decide to be an astronaut, or we become satellite engineer in telecommunication engineering. You can be a satellite engineer if you know all these ones extensively. Now let's take a look at orbital motion of the planets. Now as the distance from the Sun increases, if you move away further away from the Sun's gravitational field strength will also reduce. If the distance increases, the gravity will reduce. Remember I said the gravity is larger when you're closer to the Sun. That means the gravity of Mercury is greater than the gravity of the Earth. The gravity of Venus is greater than the gravity of the Earth. The gravity of Mars is smaller than that of the Earth. It's smaller than that of Mercury. It's smaller. Because as you move further away from the Sun, the bigger the distance, the smaller the gravity. The bigger the distance. So distance and gravity are inversely proportional. I think I wrote that. Gravity and distance, they are inversely proportional. See, gravity is inversely proportional to distance. I've written that equation. So the further away you move, the more the speed and gravity. Where I wrote gravity, you can write force. You can put F here, okay? The same thing. Gravitational field strength is force, or gravitational force is force. It's a type of force. But speed and that force, they are directly proportional. For speed and that force, they are directly proportional. Speed and force, or gravity and force, they are directly proportional. Okay, meaning one increase, the other one also increase. That's the meaning of direct proportional in Greek. Okay, we say the sun's gravitational field strength will decrease if the distance increases. If the distance also increases, the orbital speed of the planet decrease. Okay, the orbital speed will decrease. Therefore, for an object to maintain a circular path, it must have a centripetal force. It must have what? A centripetal force. Now, what is a centripetal force? Is the force on an object towards the center of a circle when the object is set in motion. When the object is in motion, the force that acts the object towards the center of the circle is called the centripetal force. The force that pulls you towards the center of the bigger object is called the centripetal force. There's another one they call the centrifugal force, the one that pulls you away. The ones that pulls you away. For example, if you have, let's take a look at this one. Okay, this is a centripetal force that pulling you towards the center of the bigger object. The one, if there's a force pulling you away from here, it's called centrifugal force. If a force is acting you out of outer space, it's called centrifugal force. Okay, now let's quickly move on. Okay, now let's take a look at the centripetal force on the planet depends on what? The strength of the sun's gravitational field. It depends on the gravity of the sun and the distance of the planet from the sun. So the centripetal force depends on the gravity of the sun and the distance away from the sun, the distance of that particular planet. So two factors. It depends, centripetal force is depending on the gravity, the G value of the sun, and the distance of that planet away from the sun. Is that okay? Now let's take a look at this. We say the centripetal force on a planet is proportional to its orbital speed. That means it's directly proportional to the orbital speed. If the speed is high, the centripetal force will be high. Okay? Now we say that a planet is from the sun. Therefore, the further a planet is from the sun, the smaller the orbital speed. The far away you are from the sun, the smaller your orbital speed and the longer your orbital period. Remember orbital period is like time. It's like time. The farther away you are, the longer your time. Like the earth is so far from heaven, or if heaven is used as the throne of our creator is used as the benchmark, earth is so far away from it. So the longer the time we see here, we see that 100 years, we see this one, so it's just a few seconds in heaven, and so on and so forth. The farther away, the longer the time, and the farther away, the smaller the speed. Okay, so speed here is so small. That's why the people in heaven, they move with the speed of light, or even more than speed of light. Okay, they move with speed of light also. We that are so far away, our speed is so small. We don't have speed. Okay, so that's it. The farther away, the smaller the speed, but the greater the time, the larger the time, the longer the time. Let's use the word longer for time. Okay, now let's take a look at this orbital radius, speed, and period data. For example, Mercury, I think this one we are benchmarking with the sun. This trend in orbital speed and distance can be seen in the data of the planets in the solar system. Okay, you can go to NASA website to see all this information. They have all this information in their website. Mercury, the orbital radius is 57.9. This is a data file that is used for calculation. If you're looking for orbital radius of the Mercury, it's 57.9 kilometers. For Venus is 108. For Earth is 149.6 kilometers. The orbital speed for Earth is 29.8 kilometers per second. And in days, the orbital period, they are measured in days or years. Remember I told you period means time in physics. The orbital period is 365, right? Orbital period is 365 days. Okay. Orbital 365 days, right? Now, if you look for every other planet every other planet in the solar system have their own radius, orbital speed, and orbital period. Okay, so it takes Neptune 165 years to orbit around the sun. Take Neptune 165 years to orbit around the sun. It takes Uranus 75 years to move around the sun. For us, it's 1 year, which is 365 days. Okay, for Earth. It takes Saturn 29.5 years to orbit around the sun. It takes Jupiter 11.9 years to move around the sun. It takes Mars 687 days to orbit around the sun. It takes Earth 365 days to orbit around the sun. It takes Venus 225 days to orbit around the sun. It takes Mercury 88 days just to move around the sun. Okay, so I think this is all for today's class, and thank you for joining us.